Howdy all, and welcome back. This is Mr. Callen here to help you with Chapter 5, Lessons 8 and 9, Equivalent Fractions and Simplest Form. Go ahead and pause if you need. Check your answers. Come on back when you're ready. We'll talk about number 16 in class, but you might be able to figure that out just from what I've written. So we're going to take everything we've known. Yes, we have already done some equivalent fractions, but of course, you know we're going to crank it up a notch. So we're going to actually find equivalent fractions that are both all numeric as well as algebraic. And yes, we're going to simplify numeric and algebraic fractions as well. Now, the reason for doing this, of course, eventually you're going to get into computing algebraic fractions. Whatever the date, ladies and gents, whatever the assignment number, go ahead and pause the video, title your paper, come on back when you're ready. All right. The basics of equivalent fractions. I got a feeling you guys already understand this. Here's what we got. If you got an apple, you cut along the dotted line. What's that part of the apple? You probably already realize that. What if you cut it again along both of the dotted lines and you have two of those pieces? What do you notice? Well, you might notice that 1/2 of an apple is the same as 2/4 of an apple. It's exactly identical. In other words, you eat half an apple, you eat 2/4 of an apple, and your belly does not know the difference. That's what we mean by equivalent fractions. Same quantities, different size slices. So as you can see by the two fractions at the top, 1/2 is the same as 2/4. Think about which one is the equivalent to those as well along the bottom, and you probably already realized. I don't know what fraction this is because the slices are not even the same size, but we can pretty quickly tell that it appears to be more than a half. So 1/2 is the same as 2/4, which is the same as 3/6. All the same amounts of chocolate bar, just different size slices. Now I want you to think about why this works for a second. Let's say you want to change 3/5 to 6/10. I bet you already realize that if you multiply anything times a whole, you're going to get the same amount. Notice that multiplying by 2/2 is essentially the same as multiplying by a whole. 3/5 times a whole is still 3/5. 3/5 times 2/2 is 6/10. So that's the mathematical piece why it works. In the like manner, you could have said 3/5 times 4/4. Well, wait a second. 3/5 times a whole is still 3/5. But if you were to split those pieces up, each of those 3 cut up into 4 is 12. Each of those 5 total pieces cut up into 4 is 20. Again, that is the same amount. In fact, all of these are the same amounts of chocolate, of apple, of whatever. They're just different size slices. All right, so let's think about this. If we wanted to cut 2/3 up into 12ths, how much would we have to cut it up into? If you just analyze and say, okay, what if we multiply both by 2? Nope, that doesn't work because that only gets us 1, 2, 3, 4, 5, 6 total slices. What if we cut it up into 3 pieces each? Well, that doesn't work either because that only gets us 1, 2, 3, 4, 5, 6, 7, 8, and 9. So essentially, you're asking yourself 3 times what is going to be 12? If we cut each of these up into 4 pieces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, there we go. And you will notice that we did have 2 slices colored in, if you will, but we cut each of those 2 up into 4 slices. So we're going to get 8. In other words, 2/3 is the same as 8/12. And what you're always asking yourself is, can you identify what number that you can multiply both numerator and denominator by so that you still have equivalent fractions? In like manner, sometimes we don't want to make bigger slices. Sometimes we want to make smaller slices. In other words, sometimes we want to group slices together. So I ask myself, what can I cut up both 10 and 6 into? And I immediately notice both are even. Imagine giving 2 slices of pizza to each friend and then grouping the remaining slices into 2s as well. Well, in this case, 6 out of 10 would be the same as 3 out of 5. If you just look at the blue circles, the blue bubbles, 3 of those are colored in out of a total of 5. So it's not always multiplying. Sometimes it is dividing, or often we say reducing or simplifying. If you notice that the numbers get smaller, for instance, from 6 to 3, then you can say, all right, instead of multiplying, what number can we divide by? And in this case, it was 6 divided by 2. Of course, anything you do to the numerator, you must do to the denominator. If you divide by 2 halves, that's the same as dividing by 1 whole, and you'll get the same quantity, just different size slices. So you'll multiply if you want more slices or smaller slices. You'll divide if you want bigger slices or less. In this case, it doesn't really matter if the quantity known is on the left or the right. Now, I know some people would ask themselves, what could you divide by? And that's just fine. Then they'll say, what do we have to divide? What big number would have to be right here? On the flip side, you are always welcome to go right to left. In this case, we ask ourselves 4 times what is going to give us 16 slices? Well, naturally, 4 times 4, 3 times 4, and you'll get 12. So you're welcome to go either way. Some people would do just fine going this way. Okay, Mr. Cowan, that's all right. Other people would rather go right to left. It doesn't matter. One way or the other, you should find that 2 different fractions are the same amount of chocolate, just different size slices, equivalent fractions. Now, you probably already guessed what's happening here. We're heading toward algebraic fractions, but we're still going to have the same process, just a little more complicated. We have to ask ourselves 5ab multiplied by what will give us 20a squared b. Now, what I'll often do is just multiply and figure out the numbers first and then go back and figure out the variables. Now, you already realize that 5 times 4 is going to be 20, so of course, we need to be fair to the numerator. However, right now we only have a b, and we would like a squared b. In other words, it's going to take multiplying by another a in order to get a squared times b. All right, so if we multiply the denominator by 4a, we must be fair to the numerator. Let's check this out. 4 times 4a, 4 times 4 is 16 with a single a. You're welcome to write the one up there if you wish. You don't have to. But in this case, ladies and gents, we have now found an equivalent fraction to 4 over 5ab. Let's see if you can continue on with the next part. If you wish, pause your video and come on back when you are ready. So we're going to ask ourselves, what can we multiply 8xy by in order to get 24x squared y? Sometimes it helps to write this all out. 8 times what will give us 24? Well, we're going to need a times 3. Here we have a single x, but we want x to the second power. So we're going to need another x. And we have a single y, but we need y to the second power. We're going to need another y. So in this case, if you look at each of those blue factors involved, we're going to need to multiply by 3xy. Anything you do to the denominator, be fair to the numerator. And so we have 7 times 3, 21. And then there's just a single x and just a single y. Once again, you're welcome to write the 1 there if you wish. It is your choice. So we've now found equivalent fractions. 7 over 8xy is the same exact amount as 21xy over 24x squared y. All right, Mr. Cowan, you seem to be enlarging. You seem to be multiplying. You seem to be figuring out how many more slices do we need, but can we go the other way? And that's absolutely true that we can go the other way. Simplest form, ladies and gents, I'm going to show you a couple different things. I have a hunch that many of you can just immediately spot the greatest common factor. After all, you got skills, you're in this class. 15 divided by 3 is 5, and 24 divided by 3 is 8. And nothing else will reduce into them besides 1 is a common factor, but that never reduces anything. On the other hand, if you ever get stuck, prime factorization will return. Think about this. 15 is the same as saying 3 times 5. And 24 is the same as saying 2 times 12. 12 can break down into 2 times 6. 6 can break down into 2 times 3. And ladies and gents, don't forget what we have learned. Any number divided by itself, except for 1, or except for 0, as long as that number is not 0. Any number divided by itself is 1. And so look what remains. We have 5 in the numerator. We have 2 times 2, which is 4 times 2, which is 8 in the denominator. Prime factorization could also help you with reducing. And I have a hunch that you didn't learn that in 6th grade. I could be wrong. Now let's go on with 32 over 20. And I'm going to do this wrong. No correction. I'm not going to do it wrong. I'm going to do it the long way. Some of you notice that they're both even. In fact, you can always write the first several prime factors and just go in order. Does 2 go into it? Yeah, so let's divide by 2. Nevertheless, those are both even as well. 8 over 5. Does 2 go into that? 2 goes into 8, but 2 does not go into 5. Keep on going. 3 goes into neither. 5 goes into 5, but not 8. 7 goes into neither, and now we're too big. In fact, this is the simplest form of that fraction. Sooner or later, we will learn to change that to mixed numbers. That probably won't happen until next chapter. Nothing wrong with writing 1 3/5, but for now, I'm just going to focus on 8/5. Okay, now let's go back and use a different method, the method of prime factorization. So 32 ends up being 2 to the 5th power. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Meanwhile, 20 will break down into 2 times 10. 10 is composite, so it breaks down into 2 times 5. And now, ladies and gents, please notice that they both share 2 times 2. 2 divided by itself, 2 divided by itself, and look what we end up with. 8 over 5. Just to reemphasize that if you had noticed the greatest common factor was 4, you could have reduced by 4, and saved yourself all the intermediary steps. That is if you can just eyeball, if you can spot the greatest common factor. If you can't, no worries. Continue reducing until it cannot reduce any further. And if you're totally stuck, then go on to the prime factorization method, which always works. Now, the prime factorization method might be your best friend when it comes to algebraic fractions. I'm wondering how many people can look at 8x squared and 6xy and immediately figure out what can be divided into both. If you can, great. If not, come down and do the do the prime factorization of each. 8 can break down along with an x. 6 breaks down into 2 times 3 times x times y. We can immediately spot the fact that it will both divide by 2, and they share a factor of x as well. Now, pretend that you can't see that bottom piece, okay? 8 divided by 2 is 4, and x squared divided by x leaves us with a single x. Meanwhile, in the denominator, 6 divided by 2 is 3, and if we have xy divided by x, that leaves us with a y. Now, many of you are not going to be surprised at all, because if you take a look here, you'll see that, oh, Mr. Callan, you didn't copy down the x squared. My apologies, folks. Hey, we all make mistakes. I'm no different. So let's try that again, shall we? We divide by 2x and we get 4x. We divide by 2x in the denominator, and not to your surprise, we'll get 3y. All right, one final example before we head to our homework assignment. Yep. Let's do 9RS over 24r squared. Now I'm going to challenge you to pause. See if you can just make a prediction. What's the greatest common factor, including variables that we can divide both of those by? Pause and come back when you're ready. So 9 can be split down into 3 times 3 with an r and an s. 24 can be split down into 2 times 12, 12 split down into 2 times 6, and 6 2 times 3 with an r and another r. At this point, you can eyeball the fact that they will share a 3 and an r. If you guessed that 3r was the greatest common factor, you're in great shape. Now again, act like you can't see the bottom. 9 divided by 3 is 3. R divided by r, those r's will cancel out, leaving a single s in the numerator. 24 divided by 3 is 8. And we have r squared divided by r. Again, if you need to take that off to the side just to envision it, it's going to leave a single r. But of course, many of you are not going to be surprised. Look what is remaining in the numerator when the 3 and the r cancel out. Look what's remaining in the denominator when the 3 and the r cancel out. So this fraction in simplest form, we could divide by 3r in both the numerator and the denominator. A student with strong skills can do one of those methods. A student with the strongest skills can do both of those methods. So go ahead, again, whatever the date is, whatever the assignment number is, I want you to tackle the rest of this assignment. If you're in class with me, I might try to check these two problems. But if you're not in class with me, if you're taking a look at this at home, go ahead into page 139 and then 141. Take care, folks. Do well. Let's grow.